It's my privilege to introduce Professor Matthew Gaunt of the University of Cambridge. He hails originally from Stafford, England, although he didn't want me to mention that. He got his bachelor's degree at the University of Birmingham, his PhD then at the University of Cambridge. He then did a postdoctoral fellowship with Amos Smith at nearby University of Pennsylvania. He then rose through the ranks back at the University of Cambridge, where he's now a professor. He's also been decorated with a number of awards, including the Novartis Young Early Career Award, the AstraZeneca Award, and most recently the Royal Chemical Society Corday Morgan Medal. This is an interesting award. I did a little research on it. The first award winner was Derek Barton in 1949. The citation for this award for Professor Gaunt read, for his key advances in enantioselective synthesis, palladium-catalyzed CH functionalization, and pioneering research in the field of copper catalysis in diaryl iodonium salts. Please join me in welcoming Professor Matthew Gaunt, University of Cambridge.
Okay, well, thank you very much for the introduction, and I'd like to start by thanking Marissa and the organizing committee for the invitation to come here to tell you about some of our science. I can't say when I saw the schedule that I was over-enamored by the fact that I was going to be following Dave this morning, and after the talk as well, I am even less keen on following that. But anyway, I thought in the theme of Dave's presentation, I should also start mine with a proposal, and I think this is a proposal, a question that the community could frame, and is how do we slow down the advance of David McMillan's research? Because I did try to think about some jokes I could make about switching the lights off in the Macmillan lab, but I wasn't really sure if that was going to work. But I seem to have got something on the screen which shouldn't be there. Do you want to switch off my network? Okay. What was I going to talk about? Right. So I'm going to tell you today about a story in our lab which has been going for a couple of years. Most of the chemistry I'm going to talk about is not published. I'll start with some introductory slides just on our background to the area, but I'm going to try and show you how this program has evolved to the point where we were actually quite excited about some of the things that we can do now. And this really revolves around the chemistry of amines. And I'm going to have to ramble for a while because I actually do need the next slides as a prop for this. So, and the chemistry that we've been doing has really evolved CH activation. And I think with amines, and in particular aliphatic amines, I think I don't really need to give too much introduction as to why these molecules are important. They exist in a huge number of biologically active molecules, ranging from pharmaceuticals to natural products. And what I'm going to focus on in particular is the aliphatic framework of amines. So at this present time, we're not so interested in aromatic substituents directly attached to the nitrogen, merely the alkyl substituents, because this is an area that, in terms of synthetic methodology, is largely being overlooked because people obviously want the aromatic frameworks in many drugs, but when you think about the shape and structure of aliphatic systems, you can in principle get a large amount of structural data into, or information into these molecules, which makes their synthesis and their functionalization an important challenge. Now, when you think about how do we make aliphatic amines, there are some extraordinarily powerful methods available in the literature that have been used over and over again, and we use many of these methods ourselves. And they involve things like reductive amination methods, which is probably the most common, alkylation methods, hydroamination. And there are, of course, it's not that these are the only methods. There are things like biological reactions. Transaminases really are now giving us access to a whole different class of chiral amines, which we were struggling to make by other methods. But when you think about how important this motif is, it's still kind of surprising that there's actually not that many general methods, really only 3 or 4 general methods to access this incredibly important framework. And so we were kind of interested in taking sort of a slightly different approach to this, based on not actually forming a carbon-nitrogen bond as part of the amine framework, but more about taking readily accessible, simple amines, and then finding a way that we can turn these in a single step into more complex variants via CH bond activation. So shown in this slide here is just a very simple system that enables us to take a very simple amine, activate one of the CH bonds in the periphery of this system, and turn it into our complex product, which we'd hopefully be able to tailor to whatever needs we were interested in. Now, I don't want to spend a great deal of time introducing CH activation. I think probably most of this audience is well aware that it's a very important field, essential, in my opinion, to the future of synthesis, and we're certainly going to see a lot of talks, I think, that touch on this. We've already seen some aspects of CH activation in the previous presentation. And so I like to feel this is very much a community effort. I tend to change this slide depending on the audience I'm giving it to, just in case so I apologize if I've missed anyone out. But there's lots of different metals which can be used. We've even seen that you can just use light as well to do CH functionalization. But I think this is a community. It's quite a strong community that people in general tend to work on distinct areas, which together, taken together, can at least begin to address this sort of long-term problem of how do we really make molecules in a very, very efficient fashion. So without doubt, the most I guess powerful method, I think would be fair to say, in CH activation is the idea of using a functional group within your molecule, a polar functional group, to do CH activation by a process called cyclometallation. This is very simply where a polar functionality binds to a metal and steers it to the site of reaction. So it's essentially a reaction driven by proximity. So the most common pathway for this is through 5-membered ring cyclometallation, and in general this is a process which is kinetically favored. And it would be fair to say, I think, that palladium is probably the metal which has had most success in this field, and I'm actually going to focus on palladium today in this talk. But basically, you can cleave the CH bond to form a much more reactive organometallic species, and then you can do some functionalization step which will ultimately lead to your product. So when you think about the different groups that you might use to direct this CH activation event, we tend to look at things like carboxylic acids. That's probably the most synthetically versatile method. Pyridines are without question the most powerful group at directing metals, and these methods are very useful if you actually want a pyridine in your molecule. But if you don't want the pyridine there, you do have to deal with that at some stage, and so there is a consequence of using pyridines. Other functionalities, perhaps not quite so common, but certainly emerging. A hydroxyl group is a direct function to steer CH activation is still in its early stages, but there's now really sort of nice methods starting to emerge which can use alcohols as well. But there's actually quite a surprising lack of different chemistries in the area of amines. And this is surprising, and I'll talk about this in the next couple of slides. This is quite surprising because I think we all know amines as being nucleophilic functions which are definitely going to bind to metals, probably too well, actually. And so actually when you see the methods which are in the literature on amine directed CH functionalization, these amine functions are very much attenuated in their reactivity. They have electron withdrawing auxiliaries on there which essentially reduce their nucleophilicity. And these reactions work quite well, and in particular the work by Olaf Dorgulis has used this picolinamide auxiliary to great effect, and it's been used by many others as well. But really, I think this group has been instrumental in enabling a lot of exciting chemistry in this field. But I think if there's one small issue with this, it's not exactly the easiest group to get off afterwards. And so this is something which I think we've always tried to think about in our work. CH activation is great, but if you have to spend a lot of work putting an auxiliary onto your amine to do the CH activation to then take it off, you do slightly detract from the overall process. And it would be much nicer if you could just use the functional group directly as the directing functionality. So one of the things we really wanted to try and do is get away from these bespoke auxiliary groups and just think about using the amine itself. And as I just mentioned before, we know that amines bind very well to electrophilic transition metals. In fact, you can actually put this into context in their steric properties such that primary amines bind extremely strongly to electrophilic metals, and in fact, they actually don't fall off the metal either, which is a big problem in this area. Whereas more sterically hindered ones, tertiary amines, you can sometimes use these in CH activation reactions because the size of the three substituents essentially affects that equilibrium of how well this amine binds to the metal. There is another problem with using amines, and actually this is a very common mechanism in the reduction of palladium-2 salts, is that you can, if your amine has a beta hydrogen, then in principle you can get a syn relationship between the palladium and the CH bond, and that can lead to a beta hydride elimination event, which essentially oxidizes your amine to the iminium species, and of course that will cleave most likely. And of course we know we use triethylamine a lot to do this reaction, as I said, to reduce palladium acetate down to palladium 0 for cross-coupling chemistry. So we're going to have to deal with this beta elimination problem as well. So this is sort of how we thought about this problem. I mean, there's virtually no examples of sort of unprotected amines used in CH activation. And so when we formed our sort of hypothesis on this, we really just thought about what are the key steps. So we knew that the first thing that would happen is an amine should bind to palladium to form this monovalent or monoamine palladium species. But we knew from the literature that the next thing that happens in a very fast process is that a second amine is going to bind to that palladium species to form these bis-amine palladium-2 salts. And traditionally, these are the molecules you tend to isolate very easily from these reactions because they're extremely stable and appear to be the sort of a thermodynamic minimum in this kind of process. So this, in principle, it should be catalytically inactive because you need, or at least it's going to sit off cycle, because empirically for the kind of CH bond cleavage that we're interested, concerted methylation deprotonation, we need a vacant site, which is represented by this kappa-2 bound acetate, to actually do the CH activation. So we need to make sure that we're at this stage here and not at this bis-amine salt. And then once you undergo the CH bond cleavage, it should be relatively straightforward to functionalize that carbon-palladium bond in a way which we can change and do different transformations. So it really comes down to this how do we avoid this very stable palladium-2 species? So the kind of proof of concept experiment that we did was, if you like, a way of loading the deck in our favor. I mentioned that sterics are kind of important in affecting this equilibrium. And so we took what we considered to be the most hindered readily available amine that we would be able to get our hands on, TMP. Most of us use it as a base, as a lithium amide derivative. And when you mix this with palladium-2 salts, what you get is this, exactly what we expected, this bis-amine palladium acetate species, and we have a crystal structure of this. I'll come back to this in a second. And this was pretty stable, but actually if you warm this salt in an NMR tube, then it undergoes a rather unusual reaction, such that we believe that one of the amines does in fact fall off to create the vacant site, and then it undergoes cyclomethylation to this 4-membered ring Pallada cycle here, which when we discovered this, and we have a crystal structure of this as well, so there's the 4-membered ring there. It turns out that this is actually an extremely rare example of an amine-directed cyclomethylation, and certainly the first that we see via a 4-membered ring. So the only other comparable example, if you like, is actually on phosphines, and it's not so surprising that you might expect a phosphine to be easier in doing this because, of course, a phosphine is slightly bigger than the amine. But this was involved in a ligand activation as part of some work that John Hartwig and others have observed before. So one of the things we started to think about in this was how are we going to overcome this problem, which is going to essentially stand in the way of the CH activation. And I come back to this bis-amine complex here. So this is the same crystal structure, I've just put the hydrogens in. So one thing which we noticed was, this is the NH of the amine, okay, and there's the palladium. And we noticed that in all of the crystal structures that we have of these bis-amine palladium salts, there appears to be a hydrogen bond between the acetate oxygen and the NH. Now, you've got to be careful with crystal structures for two reasons. First of all, there's a reason why they're crystal structures. They're obviously very stable. They may not be catalytically important. But this was something, you also, of course, have to be careful where the hydrogen is, because obviously you don't always see that. But in all of the systems we always see the nitrogen apparently pointing the H at this acetate oxygen. So we were pretty confident that there was actually an interaction here. And we think actually this is possibly the reason why this cyclomethylation works, because that hydrogen bond actually locks the conformation of the amine with respect to the acetate ligands on here. And you've got to remember that the CH activation precursor is not this bis-amine complex, it's the mono valent palladium complex that I drew on the previous slide, but that hydrogen bond should still be present in that species as well. And we think what happens is that the groups on the substituents on the amine are now just perfectly oriented for CH bond cleavage by the acetate-assisted deprotonative mechanism. So this became kind of crucial to our hypothesis, if you like, in terms of how this was going to work. And so we can just change our slide slightly so that now you see this hydrogen bond here holding this amine in place, such that the acetate ligand can now undergo the cleavage to this cyclopallidated species. Now, that's a stoichiometric reaction I showed you in terms of cyclopalladation, and it would only really be interesting if we could do catalysis with this. And it turned out that this was relatively simple to take forward. And here you see an example of a carbonylation reaction. We simply put this under a CO atmosphere, use a second oxidant in the system, which is copper, and we do the reaction under an air atmosphere. And that forms these beta-lactams, which is a slightly odd structure in terms of their kind of substitution patterns. They're sort of quite distinct structures here. But you can do them on a range of systems, and we chose to try and address this from the context of heterocyclic species, which we felt would be broadly represented in pharmaceutical agents, so piperazines, morpholines, piperidines would be, we hoped, important structures. But we can also do these on acyclic species as well, and the reaction works equally well. Now, one of the beauties of palladium is that you can access a range of oxidation states, and so whilst the carbonylation process goes through the palladium 2, palladium 0, palladium 2 shuttle, you can also use slightly stronger oxidants to promote the palladium to the palladium 4 oxidation state, and then hopefully the reactivity of that carbon-palladium bond will enable you to do different transformations. And simply using this hypervalent iodine oxidant, we can now do essentially acetoxylation chemistry, so making a CO bond on acyclic or on cyclic systems. They both work reasonably well. Now, I didn't really allude to this on one of the previous slides, but this lactone here is a little different to the other amines in that it's not symmetric. So there's two sets of metal groups in this, and they are obviously differentiated by the presence of this carbonyl motif. And it turns out that when you do very similar reactions to the acetoxylation, i.e. you just use this hypervalent iodine oxidant, then we don't get the acetoxylation product, we actually get an aziridination to form this species here. And I'll just show you a couple of examples. This work is published, so I don't want to go into too much detail. But it gives you, again, a very small molecule with a high level of information. And I guess my favorite substrate on here is actually the one with the lowest yield. But actually, if you look at this molecule here, you've got 3 orthogonal sites of electrophilic carbon. And you can imagine actually functionalizing those in a variety of ways to give you access to, again, quite small molecule, fairly novel amine frameworks. Now, this is a reaction that we've actually spent some time studying the mechanism of. We don't always study in such detail the mechanism of our chemistry, but in this particular case, we felt such a study would be prudent for a reason which I'll come on to in a few slides' time. Very basically, we found that there's a kinetic isotope effect associated with this, which suggests that turnover limiting step is either CH activation or before CH activation. Other basic parameters is it's 0 order in oxidant. It is, well, at the start of the reaction, if you study initial rates, it's actually a -1 order in substrate, and that is at least partly explained by this amine complex sitting off cycle at high amine concentration. The amine is actually inhibiting the reaction. But as this goes towards completion, the amine essentially becomes first order. The reaction is first order in catalyst. We also found that acetic acid quite dramatically accelerates the rate. Now, we actually generate acetic acid at 2 stages in this process, one in the final oxidation step and one in the CH activation step. So in principle, you could argue this reaction might be autocatalytic in acetic acid, but actually what we find is that if you had 20 equivalents of acetic acid, you get a pretty good rate enhancement, which ultimately has allowed us to re-optimize our conditions. So we tend to use now 1 mol%, though it turns out you can actually use 0.1 mol%. You just have to wait a little bit longer for this reaction to go to completion. 2 equivalents of the oxidant, 20 equivalents of acetic acid. And now we can even do the reaction in ethyl acetate, and it works in reasonable yield on a multi-gram scale. So this whole process was really investigated so that we could get towards designing maybe asymmetric ligands for this process. Now, it turns out that all of these mechanistic studies were completely useless in our ability to design an asymmetric system, although we have actually discovered that you can do this reaction asymmetrically. Unfortunately, we spent 6 months studying a mechanism when we should have just screened catalysts in the first place. So this is kind of an interesting reaction for asymmetric catalysis because you only need to do one substrate. If you change your starting point from anything other than the dimethyl at this position, obviously it's not really a substrate for asymmetric catalysis anymore. So we were quite excited by the prospect of only having to actually develop one substrate on this. And after a large number of ligands that we screened, we eventually found that actually this catalyst here, actually not this exact catalyst, there's a load of big aryl groups on here as well, but turns out that this reaction actually catalyzes this reaction, and antioselectively in reasonable yield and just about acceptable EE for this process. And that's important because these molecules, you know, if we don't do something with them, they're a little bit esoteric. But it turns out, I mean, they're aziridines, so you can do chemistry with the aziridines. And it turns out you can open this aziridine under acidic conditions. So if you just have aqueous acid, you can actually just put a hydroxyl group in there. In this particular case, we protect that hydroxyl group with the TIPS group. And then what you notice in this particular species here is that you have another methyl group, which is next to this amine. And it turns out that you can repeat the CH activation on that system to generate a much more complex aziridine. And then you can, again, open that aziridine with another nucleophile, and eventually you get through to this amino acid species here, which is a rather complex quaternary amino acid with heteroatom groups in this sort of serine type position here. And so it's actually quite difficult to think how you would make that by other methods, and now we can make them asymmetrically as well. So it actually gives you access to, again, these small molecule frameworks, which you know, they're quite unusual amino acid structures. And you can open the aziridines with a range of different nucleophiles as long as you use acidic conditions. Sort of a slight caveat on this is that we were also looking at expanding the scope of the different kind of transformations, and you know, we didn't just want to make aziridines. And this is a project which I guess I didn't really necessarily want to get into too much because we would rather develop our own ligands. But actually it turns out that using Xinquan's, I mean, well, I guess we're not Xinquan's amino acids, but he was the first person to introduce the idea of using amino acids in asymmetric catalysis for palladium CH activation. And it turns out that you can do arylation with this system using these boronic ester species. Now, these are, again, a slightly odd class of molecules. It turns out these are actually rather substituted phenethylamines, which I guess may have some interesting biological properties. But actually, the amino acid is pretty important in this particular process. The reaction actually doesn't work without the amino acid. And obviously, it's a chiral amino acid, so inevitably we did start to look at the E, and this is genuinely the best we can get to it. We've made about 60 catalysts. The only good thing about these catalysts is they're actually very simple to make. But it turns out that this is sort of the best we can get at the moment. And I think without actually fundamentally understanding how these ligands work, we're at this sort of tipping point where we can't really rationally design anything. But at the same time, we're still kind of probing around various ideas to see if we can improve this. But in principle, we can now expand the general transformation from carbonylation to acetoxylation to aziridination and now arylation as well. And so we're starting to really build up this toolkit of CH activation reactions. And so if you think about some of the molecules that you can make, I mean, these are some derivatives that we've prepared in our labs just from the aziridination processes. And if you sort of benchmark these against general classes of amines, these are the sort of common amines that you see, the different substitution patterns around the secondary amine motif. And this is what we're making. We're making amines with fully substituted carbon atoms on each side. And it turns out that these molecules are pretty much virtually unknown in pharmaceutical agents. But the amines, you'd think that maybe they would have been tested at some stage. And we think actually the reason for this is that, well, it could be that they're completely useless, which we don't yet know. But it's actually very difficult to make complex variants of these systems. And so now we have a method by which we can actually access rather intricate versions of these molecules. And we're quite interested in actually studying whether the biological properties of this system based on less hindered amines, which already have demonstrated activity, whether that increased steric hindrance can actually offer something advantageous. Now, in a drive to sort of maybe change the, how can I say, the utility of these systems, we started to think about how we could access a different class of amine, which would maybe be a little bit more useful in a broader sense. And we started to look at amino alcohols. I think probably most people accept that amino alcohols are very important in a variety of synthesis projects in terms of starting materials, but also the active nature of the actual functional group motif. And I'll show you some examples here in both natural products and medicinal compounds. Coupled to this, we really wanted to try and expand the sort of the platform of the CH functionalization to incorporate a variety of different processes beyond the ones that we'd originally discussed. But one of the problems which we were facing as a starting point here was the fact that primary amines, and I said this at the beginning, they are essentially, well, almost irreversible binders to palladium salts. And so we would need a method to get around this. And we haven't given up on doing this exact transformation yet, because I still think there's a solution to this. But actually using primary amines directly in these processes, I think is well, we haven't found a solution to that yet. But what we do know is that you can generate a secondary amine will undergo very rapid CH activation. And I guess that the amino alcohol function offers us a potential to do something that might enable us to activate these systems. So just in situ, if you like, you can take this amino alcohol and condense it with a ketone to make this NO ketal. And now you see that the steric properties of this molecule are exactly in line with what we were talking about in the previous part of the talk on these very hindered amines. So that now we should be able to undergo the CH bond cleavage, and then this is actually a pretty labile group. This actually falls off in workup. So you don't really have, well, you obviously have to put it on and take it off, but you can sort of do this as part of the overall process, which manages to just about keep the efficiency of these systems in line with what we were hoping to do in the first instance. Now, the mechanism we would imagine would have been pretty much the same as the previous ones, but I just want to point out one or two things which are actually a little bit different in this. So, first of all, these NO ketals, if you try and build a molecular model of these just with one of these plastic kits and sort of assemble it around a metal atom, they are huge. They are actually clashing across the palladium. And so we were quite confident, if you like, that these off-cycle bisamine complexes wouldn't necessarily be a huge problem, and that we should probably have a reasonably high concentration of this monoamine species. And it turns out if you do the calculation on this, that sort of bears out, and that the energy of these bisamine complexes is reasonably higher than the monoamine complex. So we were quite confident this would work out. Of course, we have this hydrogen bond, which we believe is crucial, but I'll show you in this case we can't see that, but there's a reason why we can't see that. So it turns out that when you take this amine and mix it with palladium, we don't get any of the bisamine complex which we had in the previous system. In fact, we under no circumstances have we ever been able to observe that. Instead, it goes straight to cyclopalladation, which is quite unusual for amines. And actually, this cyclopalladation happens at as low as -10 in temperature. So again, the 5-membered ring is here. For the cyclopalladation species, we can get a crystal structure of this for what it's worth. I don't really think that particularly simplifies the structure, but a lot of these things come out as trinuclear species. Obviously, these are probably not catalytically active as trinuclear species. They probably just sit, again, as thermodynamic minima, which we happen to crystallize. But it turns out that if you treat this with an oxidant, we assume we go through palladium-4, like we did previously, and that reductively eliminates to acetate. And actually, this is a pretty easy catalytic reaction to develop because all of the reagents are simply mixed together, and you can use catalytic quantities now of palladium with this hypervalent iodine oxidant, and you can generate this functionalized amino alcohol framework, which if you choose to, you can isolate it, and if not, you can just treat it with aqueous HCl, and the NO ketal falls off, and you isolate the HCl salt of the primary amine. Now, this is a pretty general reaction. I don't want to go through this in too much detail because in 3 or 4 slides' time you're going to be sick to death of this slide. But it turns out that this actually works on quite a lot of different substrates. You can put functionality in the side chain, you can vary the sterics, and in general the reaction works fairly well. It doesn't work for everything. If you have quite electron deficient groups around the amine, you do lose reactivity with this particular reaction, although I'll show you how you can get the activity back in a few slides. So you can do acetoxylation. Obviously, this is going through palladium-2, palladium-4 manifold, and so these diaryl iodonium salts, which we're very fond of in our laboratory, these also undergo functionalization, and we can now do an arylation process, and this reaction, again, is also fairly general. The one thing you'll notice here, and I'll point this out, although we don't completely understand why, is rather than cyclohexyl, we have to use this, I guess, non-obvious dimethyl system, and this one is significantly better than cyclohexyl and pretty much all of the other cyclohexyl derivatives that we've tested. It gives you about 20 to 25% extra in yield. It's more than just a stability issue, because we can make other variants of this and that should be more stable, and it doesn't necessarily help. So there's something rather unusual about the conformation of these systems which we haven't quite worked out yet. But this reaction works. You can also change the iodonium salt, and again, you can add the range of systems which we normally see in these particular cases. Now, I'm going to come back to this reaction in a couple of slides, because there's an application to that which we're quite interested in. But we could go back to the original redox system of 0,2, and we could do carbonylation reactions to form these lactams. And I told you you're going to get sick of these slides, because it works on the same systems, basically. So what's quite nice about this is that, you know, it's a pretty general platform. We've got 3 or 4 reactions now which we can do on the same starting material to give quite different kinds of products. You can just simply hydroxylate them, you can arylate them, you can then turn them into heterocycles in these pyrrolidinone cases, and you can even do, if you like, CH-HEC type processes to make a slightly different class of 5-membered ring heterocycle, and surprisingly enough, these systems tend to work fairly broadly again. So just from a single starting material, we've got 4 reactions now that we can essentially diversify the structure from, and this work is sort of accepted. I'm not quite sure where it stands at the moment, but it's accepted in principle, so it should be coming out in a not too distant future. Now, one of the things I told you about in this arylation was an application that we wanted to do. And so we made this iodonium salt, which has this greasy side chain on it. And it turns out that the framework of this molecule is actually fingolimod, which is Novartis's multiple sclerosis treatment, which is, I think, $1 billion a year drug now. And we can make this very simply from, so this is a commercial amino alcohol. It was essentially a type of buffer. In just a couple of steps, we can formulate the actual active ingredient itself. But I mean, that's not, so nobody's ever going to use this in a manufacturing sense. But we can actually do some kind of cool stuff with the CH activation, because if you start with the molecule that just has 2 ethyl groups here, which is also commercial, for example, you can start to interchange some of these CH activation reactions. So you can do acetoxylation and an arylation, or you can do, I mean, it's not so easy to see that you would get the carbonylation directly, because that's going to give you a heterocycle. But you can do these other functionalizations which enable you in just 2 steps to get a range of different fingolimod analogs. And this is kind of interesting, because it turns out that this particular molecule is in clinical trials in 7 different therapeutic areas, which is, it seems to go after a new target which has fairly wide-ranging implications. And so actually access to analogs of these systems in a simple fashion might actually be quite useful. So if we come back to this slide again, which I showed at the start, we actually still haven't addressed any of the structural requirements that you might see in these complex amines. We've still been focusing largely on this highly sterically hindered class of amines, which, whilst interesting, I guess someone else is esoteric. And so really the challenge that we started to think about is how can we get into these classes here that I've labeled A through E, because these are the bread and butter secondary amine classes, which do actually appear quite a lot in these kind of molecules. So I talked about this problem at the start, but just to re-emphasize it, if you have a less, so all of these systems, of course, are less hindered. And so if you have a less hindered amine, then that means 2 things. First of all, you're going to have at least 1 CH bond around your amine, and everything we've done so far has no CH bonds around the amine. So beta hydride elimination hasn't been a problem, but it will be a problem now. The second thing is that as you reduce the sterics of these amines, then you're going to start to reduce the impact of this sterically controlled process, which I'm promoting as being the reason for why these systems work. So we're going to have to find a way to stop relying just on the sterics of these amines. So we know that in principle this could work. And the other reason why we're quite excited to get this to work is because now, for the first time, we should be able to tap into these robust, well-developed, well-established amine forming methods. I didn't go into great detail, or in fact any detail, how you make these highly hindered systems apart from the NO ketals. But it's not always straightforward to make these very, very hindered amines. But it is really easy. I mean, even I can do reductive amination reactions. So if we can now, we've got access to huge feedstocks of amines and simple ketones, which we can couple together and then do our CH activation to access systems which you probably couldn't go directly to in a single step. Now, we tried this reaction out under the same kind of conditions that we originally ran our carbonylation under, and the reaction does work, and this is a good day, 26% yield. But it does work, and so that was quite a positive starting point. But we were fundamentally unable to improve this beyond this kind of 26-ish% yield using the original conditions. And so we started to think about why that was, and I guess we come back to this thing about sterics. These amines are no longer quite as big as they were before, and so perhaps this instability which we'd induced in the bisamine complex is no longer the driving force. And so we thought, well, what else can we put on to this system which might give us that driving force back? And the only other thing that we can really look at is how to change the ligand, the acetate ligand. So if we could make this particularly big, then we might start to force these amines to want to come off this palladium species. So we were hoping that we'd be able to get carboxylate to actually promote the dissociation. So we ran a couple of reactions. So this is our blank. This is the original conditions where we don't have any additive in. And then we add adamantanoic acid. It's obviously a much bigger acid than the acetic acid, which is going to be generated in this reaction. And we get essentially, not quite double, but we get a significant increase in yield based on the blank reaction. And I put the benzoquinone one in not because that's a particularly big ligand, again, really just for control purposes. So this does improve with benzoquinone, and I'll explain that next. But if you mix those two things together, I don't know why we used 0.4 equivalents, but we probably got there in the end. But suddenly, if you mix these two things together, it turns out that you now get quite a big jump in yield. And this reaction actually starts to become quite practical in terms of its synthetic utility. But what was interesting is that we simply cannot isolate any of the classical, well, not classical, but the four-membered ring cyclopalidation complexes, which we kind of figured must be operational in this. And it's not that we are great at crystallizing things, but with the cyclopalidation, if it happens, it does tend to crash out, or you can actually isolate it from stoichiometric reactions. And so that's made us just think a little bit about whether we were really still on the same tracks as we had been with these very hindered amines in terms of reaction mechanism. So we can make the bisamine complex. So this is we actually make palladium adamantanoate, and then we mix this amine. We have a crystal structure of this system. This is not particularly enlightening. It's shown like this so that you can maybe see it is quite crowded around this system. The adamantanoic acid does influence, to a certain extent, the positions of the amines. And if you take this bisamine complex and treat it with benzoquinone and CO, you actually get an 89% yield of this in a stoichiometric fashion of this beta-lactam. So in principle, at least we know that this must be somewhere involved in the mechanism. Interestingly, if you do the same reaction from this bisamine complex, but without the benzoquinone, you only get 26%, which is back to where we started before. So it's clear that benzoquinone serves some extra role in this process, which I'll maybe allude to in the next slide. So what we think is happening now is that CO may displace one of these amines because this whole complex is getting quite big. And CO is a pretty small ligand, it's a strong ligand. And it binds to the palladium, it maybe not in this particular form originally, but I need to get to that cis form in order to do the next step in this process. But what we think happens now is that this amine now attacks the CO directly in a sort of a 1-1 insertion, or amino carbonylation, and actually generates this acyl palladium species. Now, this acyl palladium species is quite unusual. There's one or two examples in the aromatic literature. And it kind of would make sense, yeah. It's not so surprising to think of this, but it turns out that there are very few examples of this particular pathway, and certainly nothing in the aliphatic area. CH activation now takes place through not a 4-membered ring, palladicycle, but actually a 5-membered ring acyl palladium species to form this, which must pick up benzoquinone, we think, at this stage, because benzoquinone should, in principle, accelerate the reductive elimination to form the beta-lactam. Now, we actually do have some evidence for this. We haven't made this exact species, but we have made acyl amino palladium complexes, and actually they do undergo beta-lactam formation. We just can't quite make the exact same one where we have this kind of bridging acetate. We actually have phosphines on there, but in terms of a mechanistic proof of concept, it does show that you can do the CH activation as we expect is happening, albeit in an ever slightly different system. So this, we think, is now again, it's sterically controlled, because actually if you have a very hindered amines, you don't go through this mechanism. You go through the 4-membered ring cyclopalladation complex, which I talked about at the start. But as you start to strip back the sterics, you switch on this different pathway, which actually ends up at the same product, but by a slightly different CH bond cleavage mechanism. So it turns out this reaction is actually pretty general. There's a range of systems that work here. You can vary. Actually, every time I look at this slide, I always think I should draw the amines, not the product. So just to explain, we're inserting CO between the amine and the methyl group here. So it works on a range of systems. You can have various functionalities. You can have polar functionalities. You can have sterically hindered groups. You don't always need this cyclohexyl. You can put other cyclic systems, which I guess is not a leap of faith. But you can put heterocycles in as well. And in particular, this one was quite surprising that the actual sulfur is one of our best substrates. I always thought that sulfur would poison this system. But we're taking very, very simple amines now. And this is actually one of my favorites. This is just diisopropylamine, I guess, the compound we all make LDA from. And now you can do this CH activation, 61% yield, to give this admittedly completely useless beta-lactam, I guess. But I guess when you think about bulk starting materials and actually carrying out this transformation, this is a relatively interesting example of that. But what we're really excited about is what we can now start to access in this. And so we can now take amino acids. We can take very simple, well, almost completely linear systems. So here we don't have any branching on the other side, or in case on this side either. And we can start to do that CH activation. These are all sort of ongoing projects at the moment, but these all work in greater than 50% yield at the moment, and that's just without really doing too much extra to the reaction conditions. So the fact that we can take amino acids, and I think these ones are really exciting, where we're just taking linear amines essentially, and now doing the CH activation to form these useful compounds is well, we're quite excited about this. Because when you put it into context, and these are all of the different ways that you can draw secondary amines, where we're only worried about branching. I mean, at some stage you can introduce countless stereoisomers, but we're only introducing branching next to the amine just to limit the numbers, if you like. And we can essentially do all of these. The only one we have the hit with the linear system, but the reaction is quite low. The problem here is that nitrogen actually adds to benzoquinone, and we have to strip that pathway down before we can get it to work. But all of these other ones now work pretty well in this system. And so we're actually excited. We can actually now take pretty much any secondary amine and do this CH activation reaction to what is quite a versatile product. Now, one of the challenges, which I guess is an ongoing one in CH activation, which is people tend to often just do methyl activation. But actually, it turns out that we've been able to adapt this actually much more simply than I thought, to methylene CH activation. So actually, I had a student visit for the summer from Ken Atami's group in Nagoya, and Kyohei ran this reaction, and he did something which I still don't really understand. I mean, we've heard already about why students do certain reactions, but I always thought that putting phosphines in an oxidative palladium-2 reaction was probably the most expensive way to make triphenylphosphine oxide. It turns out that it's just something quite important, actually. So the only product you get from this reaction is the methylene activation here, which gives the beta-lactam in relatively good yield for a first attempt. It doesn't it doesn't show any of the gamma lactam, which would be the much more conventional cyclopalidation product where, and we do know that you can do cyclopalidation on the terminal positions via 5-membered ring. But if it goes via this acyl palladium species, we now have a reason why it probably forms the methylene activation, because the methylene activation would force it through a 5-membered ring acyl CH activation system, whereas to go for the methyl group on the terminus, that would have to go through a 6-membered ring cyclopalidation pathway, which in principle is less favorable than the 5-membered ring. So we actually think this explains why we don't see any of the, the methyl activation, and only see the methylene activation in this particular case. Now, it turns out that triphenylphosphine is not the best phosphine for this. Actually, it's not this one either. Actually, xanthos has 2 methyl groups there, doesn't it? So actually, xanthos turns out to be the best phosphine. We've screened quite a lot of phosphines. Xanthos is rather special. We've obviously, as you can imagine, screened a lot of chiral phosphines. Unfortunately, none of those gave any EE, and frustratingly, chiral xanthos is one of the hardest classes of phosphines to make, to the extent that we haven't actually managed to make any chiral xanthos derivatives yet. So if anybody has those in their labs and is really burning to give them to us, we would be absolutely happy to receive them. But xanthos does seem to be quite special in this. But we're excited about this as well because, of course, obviously phosphines, so many chiral phosphines, eventually we will find one that works. So this reaction, again, it's still in development, but we get good substrate scope coverage. We sort of use the similar kind of substrates, I guess. So obviously, these are not particularly useful with long group. These are symmetrical ones, but you can do unsymmetrical coupling. So again, here we're already starting to getting into more linear type systems where the substitution is not directly next to the nitrogen, and some of these are actually our better yields in this process. Again, we can expand them a little bit. We can do cyclic systems, so we can make these fused systems. And finally, we find a group which, so one of the things with these systems, which one could argue is a slight drawback, is you're always making secondary amines. And none of the systems I've really shown you so far, apart from the NO acetal systems, constitute a protecting group. So you can't actually make, or it's very difficult to make the primary amines from some of those systems. However, this is the first time we've got a benzyl group to work. Now, we have to have the 2 fluorines there because competitive cyclopalidation on the aromatic ring is a problem. But if you put those 2 fluorines there, then actually this is a reasonably promising starting point. And it turns out that you can cleave that benzyl group off the beta-lactam relatively easily. The other thing that I should say about all of this is these reactions are all very diastereoselective. So, we haven't quite worked out why that is yet, but we occasionally see, this is probably, these ones here are the only examples where actually we can see appreciable quantities of the opposite diastereomer, and we know that it's the trans one from various NMR studies. So the other thing that you can think about when you get into methylene systems, on unsymmetrical ones, is that you can start to run into problems of essentially regioselectivity. So we started to set up a couple of test cases that we could, in principle, test whether we can actually control this. So here's just a model system here where we want to test whether the benzylic CH is going to be more or less favorable than the standard aliphatic CH. And it turns out that actually, disappointingly, this is not particularly selective. I guess it's pretty close to 1-to-1, unfortunately, which is kind of surprising because I guess we thought that the benzylic CH bond would be weaker and would be maybe more preferable. So that maybe actually tells us something about the mechanism. But we set up a different, a slightly more challenging test as well. Now, this one is not just an issue of regioselectivity. In fact, there are 4 different methylene CHs that you could go for here. We also have a chiral center, so we're going to introduce the issue of diastereoselectivity as well. And actually, this, quite surprisingly, was one of our quite a good results. So it turns out that it's pretty much selective for that position, next to the ester. Now, that does kind of support some kind of acidity argument, which we didn't see necessarily in the benzylic one. But not only is it regioselective, it's also fairly diastereoselective. So we pretty much get, not a single isomer, but we can isolate this as a pure compound in 73% yield. So that is this particular, well, I don't know if it's exactly this structure because we don't know what the communication between the chiral centers is yet, but it's a single isomer. So that's pretty cool that we can actually pick out now just a single CH bond, and if you count up, there's at least 8 methylene CHs, and then of course you add the methyls into that as well. You start to have quite a nice reaction. Now, the final chemistry slide I guess I'm going to show you comes back again to this one here. And I think an area that CH activation has a great deal of potential for, and that is late-stage functionalization of complex amines. Now, I would like to say that we can do all of these amines on this slide, and we can't for the simple reason we haven't tested them yet. But some of these are not quite so easy to access. But we can get hold of some of them. So this is propanolol, which is, I guess, perhaps a generic now. It's actually not quite propanolol because we have actually put a TIPS group on here, unfortunately, but we do need to do that in this particular case. But this is a marketed drug, and it turns out that the carbonylation reaction works pretty well on this. It's very diastereoselective. We don't know which methyl group it's chosen yet, but it's 15-to-1 diastereoselective in this particular case. But we have to use the conditions which were optimal for the methylene CH activation, even though we're actually activating the methyl group in this. But of course, you can imagine what you could do with that, because you can reduce that beta-lactam to the azetidine very easily using silane methods. You can just hydrolyze it to the beta amino acid, or you could just reduce it down to the alcohol. And so in a single step, you can, well, in a single CH transformation, you can access an intermediate that allows you to diversify that structure very quickly. And we're only making very small additions. We're essentially adding 1 carbon and 1 oxygen to these molecules, and then we can do some chemistry with those. So we're starting to go through those collections of molecules which we showed on that slide to see if we can actually roll that out in a more general sense. So in summary, I hope I've convinced you that we are getting towards a general strategy for the CH activation of aliphatic amines. We're actually really excited about this sort of new, well, nothing new anymore, a sort of an unusual mechanism for acyl palladium CH bond cleavage that gives us these beta-lactams. We've identified, in my opinion at least, 3 distinct pathways. One via the 4-membered ring, which I showed you at the start, and then this very facile 5-membered ring CH activation, which is the most, I guess, classical of the ones that I suppose I've explained today. And then at the end, this newer pathway, which I think is allowing us now to access all of the different kinds of amines which we might want to use. And as I said, we can do all of these systems now, with the exception of this one here, but we're confident we will have that shortly. So amines are really starting to become our friends now, whereas I think it's fair to say that amines have often been a graduate student's enemy in the past. The story I was hearing, for every nitrogen in your molecule, you should add a year to your PhD. But we quite like them. So we're looking at more complex challenges now, and also different ways of actually using amines to do CH bond cleavage, but maybe go beyond palladium. So finally, I just want to acknowledge the people that have done the work. So actually, Andy, you've already heard his name today. Actually, he was worked alongside Ben, who actually discovered this reaction as a graduate student. But Andy was the person that actually, really made this robust and powerful with the 4-membered ring chemistry, and Beatrice also assisted him on that. Daniel, Yohai, Tim, Victoriano, Jonas did the amino alcohol work. Adam is a self-taught mechanistic chemist and computational chemist. Who has done all of the and then also discovered the enantioselective selective reactions. And then this group at the bottom here have really started to expand this chemistry towards the less hindered amines, which I think will ultimately be the most important contributions from this area. Acknowledgements from the usual suspects in the UK, the research councils, and then some from industry. Finally, thank you again to Marissa for the invitation, and to the organizing committee for putting together this fantastic event. And thank you very much for your attention.
So we definitely have a few minutes for questions. And the mics are coming out, hopefully. I actually have I think probably a relatively straightforward question. The difluorobenzyl derivative, is that just taken off with hydrogenation, or is there something?
I wish it was as simple as that. I guess maybe I kind of brushed over that cleavage. We have to use a birch reduction to get that off, to be honest. So it's not the most synthetically viable reaction just yet, but it's funny actually, you can't getting benzyl groups off beta-lactam amides is actually not as straightforward as we thought. So you can do hydrogenation, we haven't got it to work on that particular system, but in principle we should be. I did my PhD on designing novel benzyl groups, so I absolutely have to be able to solve that problem.
Great talk. I was hoping you could tell us a little bit more about how Xanthos is working as a ligand. Is it because it's tridentate, or is that more of an effect of the meridional structure that Xanthos can adopt?
Yeah, that's a good question. The simple answer to your question is no, I can't tell you why, because we don't know yet. What I can tell you is that Xanthos remains intact in that reaction. So we definitely don't see the corresponding phosphine oxides, which we thought we might do. And actually, if you make those phosphine oxides and use them as ligands, they essentially don't work. So obviously, if it's bidentate or even tridentate, then we start to get into a coordination number issue at some stage. So I actually don't. I mean, palladium in the 2 oxidation state can support 5 coordinate species. There's a number of X-rays of, actually with benzoquinone as well, which may be relevant here. But at some stage in the CH bond cleavage step, my guess is that one of those phosphines has to dissociate. So it may still be bidentate because the oxygen can keep it in place, but we haven't done, I guess we're not quite sophisticated enough with our computational expertise yet to be able to interrogate that in more detail. But our current thinking is that probably the phosphine has to become monodentate at some stage. That's not a terribly good answer, I have to admit.
I was wondering if you tried any other electron efficient olefins other than benzoquinone to try to accelerate the step?
Yeah, and benzoquinone seems pretty special. We can use we can use substituted versions of benzoquinone. So actually, an interesting one we found that works pretty well is the phenyl, just a monophenyl derivative of benzoquinone. That actually has comparable yields, and so that also gives us the option to then increase the electronic or reduce the electron density on that system. Actually, it turns out that benzoquinone and simple neutral derivatives again seem to be this kind of sweet spot. So I mean, there was if you do things like maleic the systems, they actually don't work. So it looks fairly special that benzoquinone is important.
I noticed that you use carbon monoxide at atmospheric pressure. Mm-hmm. Have you tried higher pressures?
Yeah. So some of the probably should. One of the processes actually requires slightly elevated pressure. Right? We can do it in just simple glassware, but we probably operate at about 1.5 to 2 atmospheres. But if you do, you don't need to do it at higher pressure, but the reactions, they don't always work. One of the problems is balancing out the palladium, essentially presumably forming nanoparticulate palladium black. So if you have very high pressure, sometimes that can be a problem. But what we found is that you can change the ratio. So we actually use 2 different types of CO. We use either 100% CO or 6.25% CO in air, which is a commercial mix. And actually we find that frequently that's the better system to use. We don't get such heavy depositing of the palladium out of solution with the lower concentration of CO. But you can certainly do it at higher pressure and the reactions are usually faster.
Thank you.
Everybody wants to get on the bus.
Last call for questions. Run up on the balcony.
Well, we haven't done that. I mean, this is always the really easy way out of this kind of question, but it's actually true. We've only just done that reaction in the last week, so we haven't designed anything more that may be more selective yet. But what to partly answer to that, although it's not quite the comment you were making, in that particular example, we used the pivolate protecting group on that oxygen of the alcohol. That's actually, we have made the compound with tips there, and actually that's less selective. So I'm not sure if that's an electronic effect, but as opposed to a conformational effect, but you can certainly play around a little bit with the structure of those compounds. But in terms of the actual electron withdrawing nature of the ester, we haven't done anything on that yet, but we should definitely do that.
Is the acetate required in all cases, or can you use other palladium sources to start?
It's pretty important. I mean, you can start with palladium chloride, but you have to use silver acetate with it as well. So obviously, we're just getting the acetate. So we've pretty much found that, I mean, it doesn't have to be acetate, but it has to be carboxylate. You can't use, and then you have to be quite careful with the carboxylate as well. So trifluoroacetate, that pretty much doesn't work in any of these reactions. Pivolate works, benzoate works, obviously adamantinoate works. We haven't done the kind of in-between ones where you have sort of maybe functionalized acetic acid derivatives in terms of heteroatoms, but I'm sure they will work. But at some stage you have to buy in sort of synthetic efficiency of the overall process to how much tinkering you want to do with those additives. But it does have to be carboxylate.
Let's thank Professor Gaunt
for his great talk.
All right, just a couple of real quick announcements. So the tour buses to DC will start departing the Clarice a little after 11:45. We're going to start loading right away. And then if you want to pick them up in front of the dorms, we'll have one bus go to the dorms to make sure we don't lose anybody. And then for those of you that aren't going to Washington, we have a couple of things this afternoon. From 1 to 4 p.m. on La Plata Beach near the Epley Rec Center, we have Frisbee, volleyball, and soccer. And it's a beautiful day outside. It's absolutely gorgeous. We reconvene at 6:45 p.m. for our evening session, and the poster session runs from 8:45 to 11:30 p.m. tonight. So have a great afternoon, everybody, and let's thank both our speakers again.